Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome students. In the previous lecture we have discussed two important parameters, namely poles and zeros, and in this lecture we will discuss first order systems. So here order of the system means the order of the equivalent differential equation that represents this system, or we can say the order of the denominator of the transfer function after cancellation of the common factor in the numerator. We will discuss the first order system without zeros, because we have seen earlier that the system 0 contributes only to the amplitude of the component parts of the total output response, whereas the poles of the system contribute to the form or the shape of the output response. In first order systems we have only one pole. This is an example of first order system. So if we plot it, then it output response for the step input will be look like this. So if I change the value of this pole, for example I am increasing the value of pole, then the effect is the response will be faster than the previous response. Means by increasing the value of pole, the response speed of my system will increase, or if I am decreasing the value of pole, then my response will become slow. So in first order system we have only one pole, and by changing the value of this pole we can only alter the speed of the response, or in other words we can say that the time required by the system to reach the steady state. The first order system without zero can be described by the transfer function a upon s plus a. This is a generalized transfer function. R of s is our input and C of s is our output. So in this transfer function we have no zero and only one pole, which is equal to minus a. If we want to find out its output response, so for that we have to apply an input, and I am applying a unit step input here. So by applying the unit step input, our output response will be C of s is equal to R of S, G of S. So I am placing 1 over S for the input and A upon S plus A for this transfer function. So if we want to find out the output response, we have to perform the partial fraction over here, and for that A upon S and B upon S plus A. Now to calculate the values of these constant A and B, I am multiplying both sides of this term by the denominator S plus A. So we will get here only A, because this S and S plus A will be cancelled by this multiplying term, and here we get A of S plus A, and here we get B of S. So here now I am saying it equation 1. So to calculate the value of A, I am putting S is equal to 0. So equation 1 becomes A 0 plus of A, because S is 0 and this term becomes 0. So here we will get the value of A equal to 1. And for the value of B, I am putting S plus A is equal to 0, or S is equal to minus A in equation 1. So equation 1 becomes here A, this term becomes 0, and here I put minus A. So the value of B will be minus 1. By putting the values of these A and B in equation A, we will get our output response as 1 over S minus 1 over S plus A. Now if I am taking the inverse Laplace transform here, and my output response in time domain will be, here I get 1 and here I get e की power minus at u of t. If I plot the pole plot over here, S plane, so we have two poles. One pole is at origin and another pole is at minus A. So it is clear that the input pole at origin is responsible for this one or this force response, while this pole, system pole minus A, is responsible for this exponential term, or we can say it as transient response. So I can write it as our system output response will be the sum of force response and the natural response. So here the force response is equal to 1 and our natural response is equal to e की power minus 80. Here we have only one parameter a, and by changing the value of this parameter a, we can alter the speed of our system transient response, or we can say natural response. So if I put t is equal to 1 upon a in equation 2, I am saying it as equation 2, then we will get our output response as at t is equal to 1 upon a e की power minus a 1 upon a, which will become e की power minus 1, and if I calculate its value, so e की power minus 1 is equal to 1 minus 0.37, and the final answer will be 0.63, or I can write it 63%. So at time t is equal to 1 upon a, the output is equal to 0.63, or we can say it is equal to 63% of its final value. The time t of 1 upon a is known as time constant. We can define time constant as the time that is taken by the step response to rise to %, of its final value. What does it mean? So I am referring to this figure. This is the step response of a first order system. Here the time 1 upon a, this time is our time constant. So the time constant is the time required by our output response to reach at this point, which is 63% of the final steady state value. The unit for the time constant is second, and 1 upon a is our time constant and its unit is second. If I take its reciprocal, then its reciprocal will be a, and its unit will be 1 upon second. So 1 upon second is also known as frequency. So we can call this parameter A as exponential frequency. Exponential frequency. We can say that the time constant is basically the transient response specification for a first order system, since it is related to the speed at which the system responds to a step input. Now let us discuss some other transient response specification as well, that are rise time and settling time, and we can show them over here in this picture as well. The settling time is represented by this arrow, and the rise time is represented by this term. First we discuss the rise time. The time for the waveform to go from 0.1 to 0.9 of its final value. We can see it graphically as over here. This time TR represents the rise time, and if we want to calculate its value, we have to find the time when our response reaches to 0.9 value, and also we have to find the value of time when our response approaches to 0.1, this value. So when we subtract the value of time at 0.9 with the value of time at 0.1, we will get our rise time. So now we calculate it as our rise time will be equal to the value of time when our output response approaches to 0.9 minus the value of time when our output approaches to 0.1 value. So I'm using equation number 2, which is C of t is equal to 1 minus e की power minus at. This is the step response of our generalized first order system. So for calculating this time, I am putting here C of t is equal to 0.9. then this equation 2 becomes (0.9) equal to 1 minus e की power minus 80. So we have to calculate the time over here. So I am separating the time term here and then taking inverse Laplace transform, taking anti-log over here, both sides. So here we get minus 80 because anti-log and log will be cancel each other, and here we get ln of 0.1, and ln of 0.1 is equal to minus 2.31. So the value of time will be equal to t equal to these both minus terms cancel each other, so 2.31 upon a. This is our value of time at when our output is at 0.9 of its final value. And now again we use the following equation number 2, and now we put c of t equals to 0.1. So now equation 2 becomes 0.1 equal to 1 minus e की power minus 80. Again we solve this equation for time, so I am separating the time term, and this will become, so again in taking anti-log both sides, so here we get minus 80 and here ln of 0.9, which is equal to minus of 0.11. So again these both minus terms cancel each other, and our time will be 0.11 divided by a. So we get our both the answers for time. Now we will subtract them to get the rise time. As shown, as we discussed over here, this time when our output is at 0.9, and the time when our output is at 0.1. So 3.1 divided by a minus of 0.11 divided by a. So the formula to find the rise time of first order system will be 2.2 upon a. After discussing the rise time, we will now discuss the settling time. The time for the response. To reach and stay within 2% of its final value. We can also see it graphically in this picture. This time t of s is our settling time, and for this case we can also say it as the time when our output reaches to this 0.98 value, because 0.98 value lies in 2% of the final steady state value, or in other words we can say that when our output response value starts from 0 and approaches to 98% of the final steady state value. So if we want to find the value of settling time, we have to find the value of time when our output response value is 0.98 in this case, because in this case our final value is 1 and its 98% is 0.98. So we can calculate it over here. The settling time is equal to the time when our output response value is around 0.98. I am again using equation number 2 here, which is C of t equal to 1 minus e की power minus at. So to find the value of time, I am putting here C of t equal to 0.98. So for C of t equal to 0.98, this equation becomes 1 minus e की power minus at, and if we want to solve it for time, we have to separate the time terms. Taking antilog both sides, so it will become minus 80, and here ln of 0.02. So the value of t will be minus of 3.91 divided by minus a. These both minus sign will cut each other, and the final value is 0.9 upon a. So our settling time Ts will be approximately equal to 4 upon a. So this is the value, this is our settling time. Now we will solve an example. A system has a transfer function g of s equals 50 over s plus 50. So we have to find the time constant TC. Time constant is represented by TC, and settling time is represented by TS, and rise time is represented by TR. So in this example we have to find these three times. So we know that our generalized transfer function is look like a upon s plus a. So I am comparing our system transfer function with our generalized transfer function. So from this we get the value of a. Here a is equal to 50 in this case. So now we can calculate our time specifications, because all the times values depends on the only parameter, that is a. So the formula for settling time is 4 upon a. Here settling time is only dependent on a, and in case of rise time it is also depends upon a, and time constant is 1 upon a. So we can calculate our values very easily over here. Our time constant TC is equal to 1 upon a, which is equal to 1 upon 50, and it will be 0.02 seconds. And settling time is equal to 4 upon a, which will become 4 upon 50, so 0.08 seconds. And the rise time is 2.2 upon a, which will be 2.2 divided by 50, and this will be 0.044 seconds. So this example, we came to know that our system will reaches to 63% of its final value in just 0.02 seconds, and it takes around 0.08 seconds to reach to 98% of the final steady state value, and from 10% to 90% of the final value it takes 0.044 seconds. In the next lecture we will discuss how these time specifications, that are rise time, settling time and time constant, help us to identify the transfer function of an unknown system. Thank you.